Hello, hello, welcome back. All right, in this video, I'm going to show you how to start the arrow problem, which is the third problem from worksheet 2. This one right here. Okay. Now, I gave you a hint in class that the way to solve this problem was to start by determining where the first arrow is when the second arrow is fired. So first off, let's read through this problem. An arrow is shot vertically upward with an initial velocity of 49 meters per second. After 3 seconds, another arrow is shot vertically up from the same spot, but this time with an initial velocity of 39.2 meters per second. Question A, how long after the second arrow is shot upward do the two arrows pass each other? And B, how far above the origin will the two arrows be? So this one is asking us for the time after the second arrow shot, not after the first arrow shot, but the time after the second arrow shot when they pass. And this is asking us for the height that the second arrow, well, they'll both, where both arrows will be when they pass. So what we have to do is determine where the first arrow is when the second arrow is shot. Because at that point, all of our T's and S's can be related much more easily. So our first task is to look at the very beginning of this problem and get information about arrow 1 and determine what we need to about arrow 1 when arrow 2 is shot. So to start off, I'm color coding this. So I've drawn a little diagram here. Purple is the initial set of arrow 1. Okay. Then when arrow 2 is fired, arrow 2 is in blue. Everything for arrow 1 after arrow 2 is fired is going to be green. And that will become a little clearer as to why I'm doing that here in a second. So I've made 3 tables over here, 2 for arrow 1 and 1 for arrow 2. And I'm going to fill these out as we go. So first off, purple, this is the stuff for arrow 1 at the very beginning. So the initial velocity of arrow 1, we're given that in the question, 49 meters per second. So this is going to be 49.0 meters per second. The final velocity of the arrow, well, we don't know that. The acceleration of the arrow, we do know the acceleration. The acceleration of the arrow is the acceleration of any free fall object because it's not being acted on by anything other than the force of gravity, so its acceleration has to be negative 9.8. And I forgot the negative sign immediately. Started writing without the negative sign. Negative 9.8, and we're going to put a 0 on the end of that to keep it at 3 sig-figs, meters per second squared. Time we'll come back to. S we'll have to come back to. Okay, with what we've been given, this is what we know about the instant the arrow is fired. The acceleration is constant throughout the entire problem, so we won't have to deal with that, which is handy. We need to know, though, the information about arrow 1 when arrow 2 is fired. So at what time was arrow 2 fired? Well, it was fired 3 seconds after arrow 1 was. So we need to know information about arrow 1 3 seconds after it was fired. So our T here is going to be 3.00 seconds. And that will allow us to determine the velocity of arrow 1 when arrow 2 is fired. And it will allow us to determine the height of arrow 1 when arrow 2 is fired. Now, we are taking the initial height of arrow 1 to be 0. We're calling the bottom of the problem 0 for this. So, we can use our first kinematic equation. V, is this on screen? Yes, but it can't be seen right there. VF equals VI plus AT. Cool, that's all on screen. And from that, we can determine the final velocity of the arrow, or the velocity of arrow 1 when arrow 2 is fired, which should be less than the initial velocity. So the final velocity is what we're looking for. The initial velocity is 49.0 plus an acceleration of negative 9.8 times the time of 3.00 seconds. And I'm cheating because I'm running out of space. So we need to multiply these two and add. So I'm going to do that real quick. And that comes out quite conveniently to exactly 19.6 meters per second. So our final velocity is going to be 19.6 meters per second. So then all that's left for us to find is the height of the arrow. And for that, our best option is going to be to use the third kinematic equation. And when am I going to be off the screen? Okay, so as long as I stay here. All right, so I'll try to stand out of the way for this. So delta S is equal to VIT. Can you see that, or am I writing too small? You can see that, okay. Plus AT squared over 2. VI is not 0, so we can't get rid of this. So we're going to be filling in all of these. So S is equal to the initial velocity, 49.0 times 3 seconds, and I'm going to abbreviate that without the decimal points to save some space, plus negative 9.8 times 9, 3 squared would be 9, divided by 2. And we can plug all of this into our calculator in one go. So I'm going to do that real quick. And by the way, I'm going to issue a challenge here real quick. Practice plugging everything in one step on your calculator. Because the fewer times you round, the less rounding error you're going to have. And you can do all of that in one step, in one equation. You can plug it all in. So this gives us that S is equal to 102.9 meters. But this is the reason I'm giving you these problems as practice. That does not follow our Sig-Fig rules. We have to round that number. So we had 3 Sig-Figs in everything we used. I know I abbreviated the 3 and the 9, but these are 3-digit numbers. And same here. That's a 3-digit number, which I abbreviated to a 2-digit number. So this needs to be 3 digits. So it's going to be 1, 2, 3. This is going to be our last Sig-Fig. 9 is going to make this turn into a 3, so 103. And then this will become a 0. Since it's after the decimal point, we just drop it. So 103 meters is going to be our S. So our first arrow is 103 meters above the ground when arrow 2 is fired. From here, it's exactly the same as the speeder problem, except that now both objects are accelerating. So I will give you, like I said, I'll give you a little more information. I would like to pause, or I want you to pause now, and attempt to fill out the information that we know for arrow 2. And then I'm going to go ahead and do that as well. So pause, fill in what you can for arrow 2, and then when you unpause, hopefully I will have it filled out. 3, 2, 1. And I'm back. So these are what we know. Okay, we're given VI directly as 39.2. VF we are not provided. We do know A. A has to be negative 9.8. T and S are what we are trying to find. So I put question marks for them. Next, you need to fill out the information for arrow 1 in the green table here. What do we know here good Lord, I can't point behind my back. What do we know over here when this arrow is fired? So what's our now initial velocity? What's our final? All the stuff that you can fill out over here. Do that now. 3, 2, 1. And I'm back. Now, real quick, I've caught a typo. There should have been a squared on this S, so I went ahead and added that. We know the exact same information for arrow 1 now that we do for arrow 2. The final velocity that we calculated here becomes our initial velocity. Becomes our initial velocity up here. The acceleration is the same. It's still negative 9.8 because it's still in free fall. And then T and S are what we are trying to find. Now, here's the cool part. We actually know the current height. So I'm going to make an addition here. SI, and I'm going to add SF down here. We actually know SI. We know the current height of this arrow. We know that it's at 103 meters relative to the ground. We do not know where it will be when they meet. And this is the trick to solving this problem. Remember, the delta here means final minus initial. So the final height minus the initial height is equal to the rest of this. So that's the key. I challenge you from here to try and solve this. I am going to pause this, and I am going to probably end up working this whole thing out. But I want you to try and do it on your own before I do. Pause it and go to another tab and open the last video, video 2, and try to work this out looking at what I did in video 2. Okay, I want you to try to figure this out from here. Okay, here's your first set of hints. Much like the speeder problem, S and T have to be the same for both arrows. So the time it takes for this arrow to go from this position to this position has to be the same as the time it takes for arrow 2 to go from the ground to its final position. So the height above the ground are going to be the same. S and SF are going to be the same for both of these. SI is 0 for this one because it's on the ground. That's why I didn't write it out. SI is 0, so SF is the only one we really need. And T has to be the same. So use our third kinematic equation and write an equation for both arrow 1 and for arrow 2. Pause the video and take a shot at that before you go on. I moved. Okay, joking aside, these are the equations that you should end up with. So I'm going to step off screen and try to print these out. So this is our initial equation for arrow 1. Delta S, so final height minus the initial height, is equal to the initial velocity. That is the velocity when the second arrow is fired, so VI from our green table over here, plus the acceleration, which is 9.8, times the time squared over 2, where T is the time from here to here, after the second arrow is fired until the 2 arrows meet. SF is the height at which the 2 arrows meet. We know SI. We know how high the arrow is at this point. We do not know SF. We don't know where arrow 1 is at this point. So we need to move S1 to the other side. So we add it to both sides to move it over. Then I've underlined in red the things that we do not know. We don't know the height, the final height of arrow 1. We do know the initial height. We do know the initial velocity. We do not know the time. We do know the acceleration, time again, which we do not know. Then, using the same equation, I did the same for arrow 2. So this would technically be SI minus, nope, SF minus SI, but SI is 0. Since SI is 0, we don't have to worry about it for this one. So the final height equals the initial velocity times the time it takes for the arrow to reach this point with this height, plus the acceleration, which is 9.8, times the t that we don't know, squared over 2. Now, I have 3 things underlined in each equation, but I actually only have 2 unknowns in each equation, just like in the speeder problem. So pause it and try to figure it out from here. Pause it now, and then I'm going to go through and explain how to get the final answer. Okay, hopefully you have an answer you've worked out. I'm going to walk through this. I'm going to go through the rest of it, unless I skip to another spot where I think you can figure it out. Okay, the first thing we're asked to find is t, so the time. So that means we have to get rid of SF. So we do the exact same thing we did in the other problem. So we're going to set both of these 2 equations equal to each other through SF. So I'm going to try and make this fit, so bear with me. SI plus VIT plus AT squared over 2 is equal to SF, which we do not know, which is equal to VIT plus AT squared over 2, where this is the initial velocity of the second arrow, this is the initial velocity of the first arrow, this is the acceleration, which is the same for both, and this is the initial height of the first arrow. We can drop this, and if we divide this entire equation by t, we can get rid of a couple of things. Wait, that might not work. Hang on, I'll get back to you on that. First, I'm going to simplify this a bit, and I'm going to replace the t's with red. So, SI plus VI t plus A times t squared over 2 equals, now arrow 2, the initial velocity of arrow 2 times the time it takes to reach the height plus the acceleration of arrow 2 times the time squared all over 2. Now, if I divide all of these by t, if I divide this by t, this by t, this by t, this by t, and this by t, this goes away, this goes away, that goes away, and these go away. So that's going to leave me with SI over t plus VI plus AT over 2 equals VI plus AT over 2. So by doing that, I have just eliminated most of my t's. Now what I need to do is I need to combine like terms. I need to get all of my t's on one side and the rest of them on the other side. Yeah, okay. So I'm going to pause this and challenge you to solve this like that, because I need a second to make sure I'm doing this right. All right, I have just finished this and confirmed that I knew what I was doing. So I need to go back real quick and make a couple of changes to this. So I apologize if this is going to mess up your stuff. But I realize that I'm setting us up for failure by not doing something. I'm going to go back and add a 1 subscript to our initial velocity, a 2, to the initial velocity of arrow 2, and a 1 to the initial velocity of arrow 1, so that we can tell these are two different velocities. Since the acceleration of both are the same, I probably should have made the acceleration red, but moving forward, that's to help keep that straight. I'm going to do the same here with the initial height. That is specifically for arrow 1. Okay, now what we need to do is we need to move all the terms that have a t in them to one side, and all the terms that do not have a t in them to the other side. So the first term that does not have a t in it is vi1. So vi1. The only other term that doesn't is vi2. So we're going to have to subtract to move this over, minus vi2 equals, this is the first term that's over here. So a, t, and you know what? I'm going to make the a red. So a t over 2 minus the other at over 2 I just marked on my hoodie. Minus si1 over t. I'm going to change my background real quick so that I have more space to work in. Okay, hopefully this should be a little easier to see since I'm not writing over text anymore. Now, we know that the a and the t here are the same, and 2 is the same. What's 5 minus 5? Well, it's 0. So these two terms will cancel each other out. And that leaves us with, I'm just going to drop everything today apparently, vi1, wrong color, minus vi2, which is equal to negative si1 over t. We now have only one t. So what we need to do then is we need to get this t into the numerator, and then we need to get it by itself. But it has to be in the numerator before we get it by itself. From here, I challenge you to come up with the answer. Pause it, get an answer, and then come back and see if I get the same thing you do. Did you do it? Did you pause it? Come on, pause it. Work it out. Don't just watch me do it. Okay. Since t is being divided, we need to multiply. So we're going to multiply the entire equation by t over 1, which is going to put t in the numerator. It will cancel here, and it will put a t in front here. Now I am going to pull my stool back over. Not that far. And step up here. So from here, we are going to come here. So t, can you see that? Yeah, okay. Not well. T times vi1 minus vi2 is equal to negative si1. We know this, we know this, we know this, we do not know this, so we just need to divide by what's in the parentheses. So we get that t is equal to negative si1 divided by VI1 minus VI2. From here, I'm going to drop the colors, do everything in one color, and I am just going to plug in our numbers. Oh, I dropped a lid. Okay. So I'm going to switch to purple for the rest of this. So now plug in numbers. T is equal to negative 103 divided by VI1 of, so that's the initial velocity of arrow 1, 19.6 minus the initial velocity of arrow 2, which is 39.2. And then we just need to calculate that. So T is equal to, grab a calculator, and the magic calculator tells us that T is equal to 5.255102041 seconds. We need 3 sig-figs in this. So 1, 2, 3. This is our last sig-fig. 5 makes this go up. So this becomes 5.26 seconds is T. That is the answer to question A. Question B is how high was it when that happened? So to get question B, we just come back over here. We now know what T is, so we can plug T in here to calculate SF. You could also use this equation, but why would you use the more complicated equation? It makes more sense to just use this one. So plug into this, that will give you SF. I'm going to pause this, let you do that, and then I will put the answer up on the board. Okay, so again, plug that in your calculator. It spits out that CSF, I can't talk. SF is 70.62076 meters. We need to round that to 3 sig-figs. Since the third sig-fig is a 6 and the fourth is a 2, we just drop this. So SF is 70.6 meters, and that is the answer to question B. Again, I want to reiterate, these are more complicated than any of the problems we are going to be going through in Unit 3. Okay, so the amount of algebra required to get through this is not unusual. Especially once we start doing Unit 3 and Unit 4, the amount of math that it's going to take to get through these is going to be pretty close to this. But you won't have to logic your way through some of this mess that you had to do at the beginning. But by the time we get through Unit 3, algebra is going to be something you have to be very comfortable with. But we are going to ease into it. So it's not going to be this big mess at the very beginning. Okay? But once we do the vector addition lab, you'll start seeing a lot more math. So I hope this helps. Again, let me know if this does not explain it. If you need help on something, send me an email. Let me know. I will get back to you. But this is the last video for today. Hope this helped. Have a wonderful weekend.